A hospital data team pulls up records for 8,000 patients admitted this year, and there's no sheet anywhere telling them which ones are similar to which. No folder labeled, "These patients belong together." Nobody handed them the categories this time, which means the first job isn't sorting into known buckets at all. It's a different kind of guess altogether, and it only gets stranger from here. Start with the most basic version of that problem, finding groups nobody named. Clustering means grouping those patients by how similar their symptoms and vitals are to each other, with no predefined categories at all going in. Unlike sorting a movie into a comedy or a thriller, there's no fixed list of group names to choose from here. The model just looks at which patients sit close to each other across dozens of measurements at once and lets groups emerge from that closeness. Patients with similar fever patterns and inflammation markers drifting toward the same cluster without anyone telling it what to call that cluster. Only after the groups form does a person look at one and say, "That's the patients with this kind of infection." The label comes after the grouping, not before it. But those groups only became visible because a computer can compare patients across dozens of readings at once. A person staring at the same spreadsheet can't see 6 dimensions of similarity by eye. Dimensionality reduction takes all those readings, heart rate, temperature, 6 kinds of blood markers, a dozen more, and compresses them down onto just 2 or 3, something an actual chart can show, without losing the shape of how the patients relate to each other. It isn't predicting anything by itself, it's a compression step, flattening a patient described by 40 numbers into a single point on a page, so the clusters found a moment ago finally become something a doctor can look at and trust. That same sense of what's normal can be what catches the one reading that doesn't fit. Though anomaly detection isn't always built this way, some systems learn normals from unlabeled data like this, others from labeled examples of past incidents, and either root ends at the same kind of alert, one vital sign spike flagged as different from everything the model has seen. Every idea so far has been about finding structure that's already sitting in the data, waiting to be uncovered. But there's a genuinely different kind of problem that gives up on that entirely. Reinforcement learning has no labeled data and no structure to find at all. An agent just takes an action, gets a reward or doesn't, and learns purely from which choices paid off over many, many tries, the way an early treatment protocol might be adjusted based only on outcomes, not any data set of correct answers to imitate. It's a big enough idea to earn its own full treatment elsewhere. For now, the difference that matters is this. Everything before this line found patterns already hidden in unlabeled data, and this finds nothing until it acts and sees what happens. Groups nobody named, a chart nobody could have drawn by hand, one spike that didn't belong, and a fundamentally different way of learning by trying. 4 ways of making sense of data that never came with an answer key.